Welcome back to this new section, Antiderivatives. Oh my goodness, we are almost done with the quarter. This section is really, more than anything else, Antiderivatives is a preview of what you will see in Calculus 2. It turns out that half, maybe even more than half, of the power of calculus lies in undoing derivatives, which is a hard thing to get your head around at first. So it's useful to take a section here at the end of Calculus 1 and give it a shot to prepare yourself for what you're about to see. All right, let's take a look here. A function capital F, and we'll be using this notation in this section, is called an antiderivative of f if f prime equals f. Right? So think about this backwards. You've got some big F, and if I take its derivative, I get little f. All right, in other words, what's going to happen is I already know this f. I already know what the derivative is. I want to work backwards to figure out what function that came from. So let's go ahead and give this a try. If I had f is cosine of x, little f, I want to find a function whose derivative is cosine of x. I want to undo a derivative. I know what that is. That is sine of x. So I'm just doing this process backwards. And a lot of calculus has to do with just doing this process backwards. Let's try this again. I want a function whose derivative is x squared. Okay, well in this case, that would be, well, think through it. What would the power have to be? It'd have to be a 3. But if I took the derivative of x cubed, I would get 3x squared. And that's off by a factor of 3, so we're going to put a 1/3 out front. 1/3 x cubed. The nice thing about antiderivatives is they're easy to check. So if I took the derivative of 1/3 x cubed, the 3 would come down. I'd get a 1, x squared. That's exactly what I got here. If I took the derivative of sine, I would get cosine. So it is pretty easy to check. However, this does fall in the world of inverse problems. There is a reason why division is harder than multiplication. There is a reason why logarithms are harder than exponents. And there is a reason why antiderivatives are harder than derivatives, and why you might need an entire another quarter just to work out how to undo this thing you've been learning how to do. With that comes a lot of power. It comes with some nice connections to finding areas and volumes, as well as some neat dimensional analysis. But for now, let's just practice this antiderivative thing. We might want to focus on something else. Is this the only answer? Is there some other function whose derivative is cosine of x? Is there some other function whose derivative is 1/3 x cubed? And I'll give you a hint. Yeah, there is actually. This is very weird, but what if I took sine of x plus 7, and I took its derivative? Well, the sine of x would go to cosine, that 7 would go to 0. Similarly, I could do 1/3 x cubed minus, I don't know, pi times the square root of 2. Pi times the square root of 2 is a constant. When I take the derivative of that term, it goes away. And so we're in this maybe new position for you where there's actually infinitely many correct answers to this. And we'd like to be able to represent all of the possible correct answers, which brings us to the most general antiderivative. Most general. Later on in Calculus 2, you'll call this an indefinite integral. Antiderivatives and integrals they're related by something called the fundamental theorem of calculus. They're basically the same thing. The fundamental theorem of calculus tells you how they are related, how area, derivatives, and antiderivatives are related to each other. So stay tuned for that in your next class. But our most general antiderivative is going to say, hey, take any answer you got, any one of these capital F's, and just add a c, where c is a constant. So what this is telling you is that if I have one antiderivative and I've got a second antiderivative, they must be related by adding or subtracting a constant. That is the whole big world of them. And hopefully I'll take a minute in some other video to address why or how this is true. Okay, neat. So our most general case is just a plus c. So this is some constant, this is some other constant, but it really could have been any constant we want. So let's go ahead and work our way through a couple of examples of this. Up top, we'll go up top here. Really, the most general example is sine of x plus some, usually is a capital C. This is 1/3 x cubed plus some capital C. Okay. If we want to find the most general derivative of 1 over x, we would say capital F of x is equal to, what function has a derivative of 1 over x? I know this one. Let's write natural log of x. Now careful on my domain here. My domain is all real numbers, and so, or sorry, all numbers except 0. So I really do actually need that absolute value there if I want negative numbers to be included. But I want this to be general, and so really we would also take plus any constant you want. Similarly for this g, this is a good one to have memorized or to learn. What if I just had some power? What is this, the inverse of my power rule? And the inverse of my power rule, well, if we think through this, I'm going to need something with one higher power, so that when I take the derivative, I get x to the n. But if I do that, that n plus 1 comes down. And I don't want an n plus 1 in front, which means I need to divide by n plus 1 to make sure it cancels out. Okay? So 1 over n plus 1, 1 over n plus 1 times x to the n plus 1. And if we want this to be most general, we're going to do a big plus c. So any constant out there you want. Okay, we will figure out situations where we can solve for that constant really soon here. Let's do a few more. Give yourself a second, see if you can figure out the most general antiderivative for these two. I'm going to roll right ahead. Hey, that 5 is just going to hang out. Just like the 5 constant multiples hang out for derivatives, that means they must just hang out front for antiderivatives. Okay, and what function has a derivative of e to the x? How about e to the x? And then a nice little plus c. Very cool. All right, I'm going to point something out here. You maybe, depending on how your brain works, you might have written this. That is also right. Believe it or not, this looks like 5 e to the x plus 5c. Now, here's a c and here's a 5c. 5 times a constant is a constant. So it's possible that if we did something, we had to go back and solve for c, we would get 2 different c's, but they would just be off by a factor of 5. So the result would be the same. Okay, so it is definitely possible to get two functions that kind of look a little different, but really all you've done is you've transformed one constant into another constant. Okay, moving on. Secant squared. What function has a derivative of secant squared? This is just a matter of you knowing your derivatives really well. So this is just going to be tangent of x and then plus c. That is it for this first video. More on this in a minute.